Okay, lads, here I'm just going to go through the homework that I said on exercise 9.5, questions 8 to 11. Right, from the start we can see first approach is get the reference angle. We know that inverse sine of minus root 3 over 2, which is given in the question, is 60 degrees. Sine is negative in the third and the fourth quadrant. If we look at our unit circle, so therefore 3 theta is equal to 240 because that's 180 plus 60. Or 3 theta is equal to 300 because that's 360 minus 60. So this is quadrant 3 and this is quadrant 4. So therefore we have to go back and put it into our general solution. General solution is for quadrant 3, it's 3 theta is equal to 240 plus n times 360. Or for quadrant 4, 3 theta is equal to 300 plus n times 360. That should be. So therefore we divide both sides by 3 just to get theta on its own, and theta is equal to 80 plus 1 n times 120, or theta is equal to 100 plus n times 120. Then the remaining steps just involve putting in different values n, so n equal to 0, n equal to 1, n equal to 2, up until the point where we go back and reach 360, because if we go over 360 all we're doing is repeating the angles and we're going to start to get these again. So key thing is find the general formula, then just substitute n until you get up to 360 degrees. Over that you're just starting to repeat yourself. So there are the angles there. Question 9 is pretty much the same. You've got a reference angle of tan is equal to 1 over root 3, that's 3 theta again, so 1 over root 3 gives us 30 degrees as a reference. Tan's positive in the first and the third quadrant, so 3 theta is either equal to 30 degrees, or in the third quadrant 3 theta is equal to 180 plus 30, which is 210. So then we work through general solution. It's going to be the 30 plus n times 360, or else 210 plus n times 360. Divide both sides by 3 again because we're asked to solve for 3 theta. We only want theta. So divides out both sides by 3 and this is what we get. Same strategy again, you just simply plug in different values of n up until the point where it starts to repeat itself. You don't want to go over 360 because you'll just start to get these angles again like I talked about in the class last week. So therefore we get our 6 angles there for theta. Question 10, a little bit more difficult. It's just because we've got an equation now, we just need to solve it. So what we do is try and keep sine of 3 theta all on its own. There. Right, we know that it was minus 1 over root 2, so therefore to look at the quadrants where sine is negative, it's negative there in quadrant 3 and quadrant 4 because it's positive in 1 and 2. So in terms of quadrant 3, it's going to be pi plus pi over 4, which is 5 pi over 4. And in terms of quadrant 4, then it's going to be 8 pi over 4, which is just 2 pi minus the pi over 4 reference, gives us 7 pi over 4. So these then are our next starting points. In terms of radians, instead of adding n times 360, we just add n times 2 pi, or 2n pi. Okay, so because in the question it gives us 3 theta is equal to, but we need to solve for theta is equal to, so we divide both sides by 3 here, and we end up getting some fairly awkward things, but just following the logic of algebra, divide both sides by 3, that 4 becomes a 12, and that's just 2n pi over 3. We do the same thing, so we do the same thing again, as I just said, put in different values of n equal to 0, n equal to 1, n equal to 2 into our general formula part there, which is the 2n pi over 3. So obviously when n equals to 0, that 2n pi over 3 just disappears. When it's equal to 1, we have to add on 2n pi. When it's equal to 2, we have to, that's 2n pi over 3. When it's equal to 2, we have to add on 4 pi over 3. So as long as we're able to add fractions, we should still be able to get to these values, even though they look a little bit awkward. Last question, question 11, probably deals with some more awkward angles, but because we're dealing with radians, but all you do is solve the algebraic equation, bring the 1 over there, the minus 1, and you get tan of 5 theta is equal to 1. From that we get our reference angle. Reference angle is pi over 4 again. Because it's equal to 1, we need to see where's tan positive. Well, tan's always positive in the first and the third quadrants. So to get a reference angle here, 5 pi is equal to pi over 4, so that's quadrant 1. And then quadrant number 3 is just going to be pi plus pi over 4, which is 5 pi. Remember, the reason for that, in our unit circle, that's going to be 0, that's going to be 90 degrees, or pi over 2, that's going to be 180, or pi, and this is going to be 3 pi over 2, or 270 degrees. Okay, so back to the question. We've got 5 pi is equal to this thing here, so therefore I divide both sides by 5. Yes, it gets a bit awkward because our first term here is dividing that by 5, that's going to be pi over 20. Dividing that by 5, it's going to be 5 pi over 20, which is just pi over 4. Last step then, all we do is just keep on putting in different values of n, up until we get to a point where we've reached 360 degrees, or up until we get to 2 pi. And that gives us our angles there. A little bit of tricky algebra just in adding fractions and things like that, and rearranging at the start, then using reference angles and stuff like that. But I agree that radians are going to be more difficult than degree measure. You can also just convert into degree measure straight away at the start and then convert back into radian measure, because you know that pi equals 180. So therefore, degrees, 1 degree equals pi over 180. Okay, so I'll leave it there for now.